All right, so this should be a pretty straightforward problem right here. We've got a 500 block of metal. Doesn't tell you what metal it is. It absorbs 5,016 joules of thermal energy, heat, as its temperature changes from 20 to 35 degrees Celsius. We want to calculate the specific heat. So really the only equation we've used so far to do this is this one, Q, heat, equals MC delta T. And we're trying to find specific heat, which is C in our equation. So if we do a little algebra on that, C equals Q divided by M delta T. Now if we go back and look at the problem, it tells us that the metal absorbs 5,016 joules. That's Q. It tells us the mass of the piece of metal, 500 grams. We want to do this in kilograms. So 0.5. And it tells us the temperature heats up from 20 to 35. So we got a delta T of 15. Remember, we're right at C degrees because that means a temperature what? Change, difference. So if we do a little calculation on that, let's take 5,016 divided by 0.5, divided again by 15. We end up with about 669. Now, remember our units on this. Joules per kilogram per Celsius degree. And I want you to know what those units mean. That means it takes 669 joules of heat, of thermal energy, to take 1 kilogram of whatever this is and do what to it? Heat it up by 1 degree Celsius. Or, if we put a negative in front of this, cool it off by 1 degree Celsius, right? Justin? Yes. That's how you're going to do the units. Now, you might have time to do one more of these before we go. Let's back up.
Do you have these online?
That's what I'm doing. I'm recording them to put them up right now. All right, let's go ahead and try it. 2 will be an easy one. We just do a conversion. We're trying to convert 20 degrees Celsius to Kelvin. You guys know that to go from Celsius to Kelvin, you have to what? Add 273.15. So our Kelvin temperature is equal to our Celsius temperature plus 273.15. So 293.15 is all we got to do. Now, when we come back from lunch, we'll do a Fahrenheit to Celsius or Fahrenheit to Kelvin kind of thing too. I don't think we've got time to approach number 3 just yet. So let me put this on pause. Alright, so we're going to work what's listed as problem 3 up here. This is a lot like the calorimetry lab thing we did the other day with the pieces of metal. We're going to take a 200 gram chunk of iron. It's initially got a temperature of 95. Put it into 350 grams of water. It's starting off at 25. And we want to know what final temperature they're going to come to. We know that the iron is going to cool off and the water is going to heat up. And eventually they'll get to what? Thermal equilibrium. We want to know what is the temperature for thermal equilibrium. The problem here gives us the specific heats of both things. This is the specific heat of water, 4180. We've been using 4186. Let's just round it off. And the specific heat of iron, 450. So on the next slide, here's kind of the big idea. The heat lost by the iron should be equal to what? Gained by the what? That's kind of the whole way the problem is going to go. For heat lost, we know that's going to be Q equals MC delta T. Over here, heat gain still MC delta T. Now the thing that's losing the heat is what? The iron. And it tells us that we have a 200 gram chunk of iron. So for mass, we're going to put in 0.2 kilograms. Tells us the specific heat of iron is 450. And temperature difference we don't know. But we know that this iron is cooling off, right? So how might we write the temperature difference? Instead of writing delta T, we might write what? Ti minus Tf, because it's cooling. And we know Ti, right? What's Ti? Yeah, it started off at 95 Celsius. So let's take Ti out there, and let's put in a 95 C, like so. And that's got to be equal to the heat gained by the water. Now the problem tells us that we have 350 grams of water. So we'll say 0.35 kilograms. The specific heat of water, 4180, 4186. We'll use 4180. And the water is going to be heating up. So how are we going to write that for temperature difference? Tf minus Ti. The Tf is what we're trying to find. Minus the Ti, it tells us that the water starts off at 25 degrees C. So now we just got to do some algebra. Solve this out. I'm going to make some space up top for us to do that. So now we're going to go 0.2 times 450 times 95. So far we went this times this times this. And when we do that, we get 8550. And our units, you see the kilograms are going to cancel. So are the Celsius degrees. So that's just going to be joules. All right, but we also have to go this times that. Got to distribute it because of those parentheses. So 0.2 times 450 is 90. So that's going to be minus 90. The units on that, the kilograms are going to cancel. That's it. So it's going to be minus 90 joules per Celsius degree times what? Times Tf. And all that's going to be equal to, over here. Same kind of thing for the water. We need to go 0.35 times 4180 times Tf. So this times this, that gives us 1463. And again, the units on that are going to be joules per Celsius degree, and that's all times what? Times Tf. And then we've got to go this times this times this. So 0.35 times 4180 times 25. And that comes out to be minus 36575, and that's joules. All right, from there we got to put together like terms. So I think what I'm going to do first of all, just to get rid of negatives, is I'm going to add this 90 to both sides. So over there on the other side, make a little space. So when I start combining like terms, add the 90 to both sides. So let's go 1463 plus 90, 1553. All that's times Tf. Now right now, here's what I still have. Got rid of my 90 by adding it to both sides. So I've got 850 joules. And then over here I've got negative 36,575. So the other like terms I can get together are just my joules. So add the 36,575 to both sides. So 8,550 plus 36,575. So added this to both sides. Ended up with 45,125 joules. And then to solve that out, I need to divide both sides by all that. Notice the joules cancel. And you said it comes out to be what?
29.
Even?
29.05.
So we need how many significant digits here? Three? Three. So 29.1. And that's it. Now one way to check yourself is you know that temperature's got to be somewhere between two temperatures you started at, right? It's got to be between the 95 the iron started at and the 25 the water started at. And it should always be closer to what? The water. Because water has what? A really high specific heat. All right, so pay attention to this problem. We're trying to figure out how much thermal energy it takes to change that much ice, starting at -5 Celsius, all the way to steam. And we're trying to get the steam to be 100 degrees. Now, there's a lot of stuff we've got to know to work this problem. First thing we need to know is specific heat of water. That's liquid water. That's the specific heat of ice. They're different. This right here is something we haven't really talked about before. It's called the heat of fusion. What do you think the heat of fusion is all about? How much heat it takes to do what to something? To melt it. It's the amount of heat it takes to melt it. Heat of fusion. So for every kilogram of water, or in this case ice rather, for every kilogram of ice, it takes that much energy, 3.34 times 10 to the 5th joules, to melt it. And then HV, what do you think that is? That's heat of vaporization. That's how much energy it takes to turn 1 kilogram of water to steam. So again, we've got the specific heat of water right here, specific heat of ice, the heat of fusion, the amount of heat it takes to turn solid to liquid, and then we've got the heat of vaporization, which is the amount of heat it takes to turn liquid to gas. With that being said, let me flip over so I have a written copy of this. All right, let's work it out. Now, this you've got to work in steps. And I'm going to do this kind of with a graph. And we looked at this graph in class yesterday. Let's say we start here. First of all, we're starting with the problem tells us we're starting at what temperature? -5. Before we can do anything, we've got to raise the temperature of that ice to what magic point? 0. So we need to get it up to 0. My board's a little off here. Here's 0. To go from -5 to 0, what equation can we use to get us from -5 to 0? Q equals mc delta T. Whenever the temperature is changing, that works for us. So we're going to go Q equals, our mass was 2,525 grams, so 2.525 kilograms. We're going to multiply that by the specific heat of ice, which is 2060. And then we're going to multiply that by the temperature change we need. We need to go from -5 to 0, so 5 degrees. So we multiply that out, 2.525 times 2060 times 5. That comes up to be, I'm going to write this up here, 2, 6, boy that board's up, 0.007.5 joules. And that's to go from -5 to 0. And once we get to 0, what do we have to do at 0? While we're at 0, what do we got to do? Heat of fusion. We've got to melt it. To calculate the heat needed for that, this equation we haven't exactly seen. It's going to be Q equals HF times the mass. Heat of fusion times the mass. So we're going to go Q equals, I gave you the heat of fusion for ice, 3.34 times 10 to the 5th joules per kilogram, times the mass, which was 2.525 kilograms. So 3.34 times 10 to the 5th times 2.525.
So that means the heat of fusion is equal to the change in temperature times the specific heat.
How'd you get that?
Q equals mc delta T, so we took out the C and delta T. Left the M.
Oh, no. Completely different thing. Here we're changing the temperature. Here we're changing the state. These Q's are not equal to each other. No, two different Q's. Still heat, but different amounts of heat. This right here is the amount of heat it takes to what? To melt. So far we've got 2 steps. I'm going to make some space now. Q equals 3.34 times 10 to the 5th times 2.525. All right, now, once we get to this point right here on our graph, what do we got once we get out to here?
We've got water.
We've got liquid water at what temperature? At 0. Now we've got to do what to the water? Heat it up. So now we got to do that. Boy, I'm just not supposed to do that up at the top. So we got to go from 0 all the way to what? 100, the next magic number. To calculate that amount of heat, Q equals mc delta T. Anytime we can measure a temperature change, that's the equation we want to use. So Q equals 2.525 kilograms. This time we're going to use what specific heat? 4180. It's liquid water. And our temperature difference is going to be 100. So now we go 2.525 times 4180 times 100. And we do get a really big number. We get 1055450 joules. Now we're going to make a note on this. This number is to take us from 0 to what? To 100. Right now, right up here, what do we have right there?
Water.
Water at 100. But it's not what yet? Not steam yet.
No, it's steamed at 100.
Now we got to steam it out. And the way we're going to steam it out is we're going to go Q equals M times what? HV, heat of vaporization. So Q equals 2.525 kilograms. I'll give them to you. You don't need to memorize it. 2.525 times the heat of vaporization, which is 2.26 times 10 to the 6 joules per kilogram. It's a lot of heat. So 2.26 times 10 to the 6th times 2.525. We end up with this number. 5706500 joules. And that is to what? To vaporize. So the answer we're looking for it wants to know how much heat it takes to do all of this, right? So we just add them up. So we go, I'll just start at the bottom since this one's already in my calculator, plus 10,554, 50, plus 843350, plus 26007.5. Add them all up, and this problem, it looks like we needed 3 significant digits. So 7.63 times 10 to the 1, 2, 3, 4, 5, 6. 10 to the 6th joules. And that again is the total amount of heat. First, to raise the ice from -5 to 0. Then to melt it. Then to raise it from water at 0 to water at 100. And then to steam it, to vaporize it. Add all those up. There's what we got. You got to know 3 equations. You do need to know the equations. I'll give you the constants. Q equals MC delta T to change the temperature. Q equals M times HF to what? Change to melt, heat of fusion. And Q equals M times HV to vaporize, heat of vaporization. All right, I want to do Celsius temperature. Our equation should be 5 knots times what? Times Fahrenheit minus 32.
Yeah.
All right, we're starting with -4. -4 minus 32 times 5 knots. That's -36 times 5 divided by 9 comes up to be -20 degrees C. I'll come back to that in a minute. Now, if we want to go to Kelvin, we need to add 273.15 to that. So -20 plus 273.15. That gives us 253.15. I don't need a calculator for that. And that's where I will stop for just a minute and do some heavy editing on this video.